Hello again, physics friends. Today we are going to focus on something called the two-state system in order to get at some of the quantifiable aspects of quantum physics. So far we have kind of talked in a qualitative way about interference using this two-slit experiment where we have a source of quantons on the left and we shoot those quantons at two slits, and on the right we see this interference pattern. And we talked about that, that the quantons are in a superposition state of going through this first slit and the second slit, and as a result, they exhibit wave-like behavior, and you get this interference pattern on the far side on the distance screen. Now, this might seem like a very straightforward experiment. You just have quantons in two slits, so it seems like there's two options. But really, what we now know is there's actually an infinite number of paths that a particle could take to get from one location to a given point on the screen, and it does not have to be straight line paths. And so to solve this problem accurately, you need to actually use fairly advanced math with integrals of so-called wave functions that describe the position of this particle as a function of time, or the probability that this particle is in any given place at any given time. And that makes use of something called the Schrodinger's equation, which is a differential equation that involves two derivatives of space of this wave function psi that represents the particle, and a time derivative as well. And so if you want to find out what is the probability of finding a particle at any given position at any given time, you basically need to solve for this function psi, and that requires some fairly advanced math, including linear algebra techniques and differential equations, and that is well beyond the scope of this course. However, essentially all of the key ideas that are contained in the two-slit experiment can be arrived at in a much more simple system called a two-state system, in which instead of having a continuous range of possible outcomes, like the position of a particle, which can take on an infinite number of possible values, we're going to focus on a different property of particles, and that property can only take on two states. Okay, and so then it becomes a very discrete calculation, either state 1 or state 2. And that does not require calculus or differential equations or linear algebra and so on. So what are these two states that we're going to talk about? We're going to build up to an actual physical system. In the meantime, we're going to do something called a cartoon system, where we're going to talk about an electron, and we're going to talk about two fictitious properties of the electron. Well, they're sort of fictitious. We're going to give them names that are fictitious, but they actually represent real properties of the electron. So we'll start by introducing one property called color. And of course, the electron doesn't have a color in the typical sense of the word, but let's just imagine that there is a property called color. And in all of the experiments ever done on an electron, only two possible values of color have ever been seen. Okay, and those two possible values are blue and white. So when we talk about experiments with an electron, we can say the only possible outcomes if we measure color are blue and white. Never red, never green, never orange, never pink, and so on. And we'll use that as our first property. So when we say a two-state system, we mean that for a given property, the value of that property can either be in one state or the other. So blue and white are the two states of this two-state system. But we're also going to introduce a second property, and that property is going to be hardness. And this hardness property, again, is a property that can take on only two values. An electron can either be hard or it can be soft. There's never been an electron that's been measured as wiggly or firm or anything else other than hard and soft. So just to be clear, we have two properties, but that's not what we mean by two-state system. The color and hardness are not the states, those are properties. The two possible states in a two-state system are the two possible values for each property. So blue and white are the two states that are possible for color, and hard and soft are the two possible states for hardness. Now, just to be clear, an electron does not have a color or a hardness, but an electron does have properties that behave in exactly the way that we'll describe for color and hardness. We're just avoiding the physics terminology at this point to get across the main ideas. Okay, so going in the future, we're going to understand that color and hardness could be replaced by, say, spin in the x direction and spin in the y direction for the electron. And the two states would be like spin up in the x and spin down in the x, and spin up in the y and spin down in the y. For now, though, we don't know anything necessarily about spin. If you do know something about spin, congratulations. But it's not necessary at this point. We want to understand the basic quantum realities for two-state systems, and then we will give those properties more appropriate names that are relevant for real electrons. Okay, so this is cartoon. This cartoon description is only cartoonish in a sense that we've changed the names for the actual properties, but all of the experiments that we'll describe have been done with real electrons and with real other quantons that have properties that can take on two states. So rest assured, you're not getting a cartoon version of quantum, you're getting the full story on quantum for two-state systems. Okay, so now we know that we have these two properties for electrons, color and hardness, and each property has two possible states or values, blue and white for color, hard and soft for hardness. Well, if we're going to do any experiments with electrons and measure these properties, we need a device that's capable of measuring the values of those properties. So we're going to introduce two measuring devices. The first is called a color box that takes input electrons and sorts them by the property of color. So we have one input and two outputs, and every electron that comes into the box makes it out, and it either comes out a blue port or the white port. Okay, and we repeat the same thing for hardness. We're going to have a device that can measure the hardness of an electron. And so we shoot in an electron. It's guaranteed to come out either the hard port or the soft port, but it doesn't get absorbed in the box or lost in the box and so on. It either comes out hard or soft, and that's indicative of the fact that every electron is either hard or soft for hardness and either blue or white for color. So every electron in makes it out. So now that we've introduced the properties of electrons, and there are two possible values for each property, and we have these symbols that represent our apparatus for measuring color and hardness, we're going to lay out a set of experiments. And I have to warn you, the results of these experiments are perhaps the most unsettling thing that I've seen in physics in a long time, and maybe even more than just in physics. What we're going to see in the subsequent experiments is that we really have to give up our traditional notion of what it means for a property to have a value. And so as unsettling as it might be to make that transition, I ask that you trust the process and see where it takes us. All right, so buckle up and here we go. All right, we're going to start with an experiment that is probably not going to be that surprising, and we'll work our way from there. Okay, so here we have two color boxes, one after the other. And we're going to send in 100 electrons of some unspecified color state. Okay? And what we observe experimentally, if we just focus on this first box, is that, let's say, 50 come out of the blue port and 50 electrons come out of the white port. Okay? It won't always necessarily be 50-50, but let's say that that's what happened. So what that means is that after this color box, we have 50 blue electrons and 50 white electrons. And the blue electrons we're just going to ignore. They're going to go up and never to be seen again, but we're going to do something with the 50 white electrons. So these electrons, they came in an unspecified state and they come out white. And we send those 50 white electrons into a color box, and lo and behold, every single one of those 50 input electrons come out the white port, none come out the blue port. So one way to think about this is to say that a color measurement is repeatable, meaning that if you measure an electron to be white and then you remeasure its color right away, it will remain white. And by white right away, I don't mean like within 5 nanoseconds. I just mean before you make any other measurement. Okay, so you measure color, and then the next thing you do is measure color again. You're going to get the same result. And that seems sensible, right? That's consistent with our understanding of classical physics, right? If you have a blue shoe and a white shoe, and you measure 100 shoes and you find that 50 are blue and 50 are white, then when you measure the white shoe later, it will still be white. That's no surprise, okay? And at some level, it's reassuring to know that this still will be true in the quantum world. Now, incidentally, all of these cartoon schematics I'm drawing are just that. They're cartoon versions of real experiments that have been done, right? So you can build an experiment that measures, say, the spin of an electron in the x direction, and if you find that it's spin up in the x direction, and then you measure out the spin in the x direction again, you will get spin up 100% of the time. So again, although color and hardness are not real properties of the electron, they are stand-ins for quantities that are real, and these experiments that I'm describing here are just stand-ins for actual experiments that have been done with quantons, not just electrons, but other quantons too. And not surprisingly, the same applies to hardness. Namely, if I measure the hardness and find that the electron is soft, and I measure the hardness of those electrons again, I'm going to get soft 100% of the time. Okay, so in come 50 soft electrons, and out go 50 soft electrons. None come out the hard port. So an electron that was measured hard and then remeasured for hardness again retains its property. So at this point, I'd like to pause and ask a question of you. Is the following possible, right? So in the last example we saw, you could shoot 100 electrons into a color box and the output could be 50-50. Is it possible to shoot 100 electrons into a color box and have the output be 30 and 70? So give that some thought. And really do give this some thought. So pause your video, think this through, and make a prediction for yourself. Write down your prediction so that you're going to commit to it, and give a reason for your prediction. I think it's possible because, or no, it's not possible because. Did you pause? Did you really pause? Okay, so let's think through this. I can come up with a way to do this. Maybe you can too. Here's how I would do it. First of all, I'll put the question a little off to the side to give me some space. And notice I now have two separate color boxes here that prepare my electrons. So I'm going to shoot 140 electrons into the first box, and I know from previous work that it is possible to get a 50% blue, 50% white output. So I have 140 in, 70 and 70 out, and those 70 white electrons are going to be the 70 that come out of the final color stage. And I also know that if I sit 60 in, I could get 30 and 30 out, and these 30 are the blue ones that are going to come out at the end of the day. So all I have to do now is connect my white output and my blue output from the previous color boxes to be inputs to my third color box. So I can definitely make this happen, 100 in, 30, 70 out, if I prepare the electrons in a known state prior to entering the color box, right? Because I know that every single one of these 70 white electrons is going to go straight through and come out the white port of this color box. And every single one of these 30 blue electrons is going to go into this color box and come out of its blue port. So I can definitely do it. And I'll introduce a term here called a mixed state, meaning that at this input here, these 100 electrons are in a mixed state, meaning that we have 70 white and 30 blue electrons. So every single one of those electrons has a definite value for color, either white or blue. But it's not a 50-50 distribution of those definite values because we have more white than blue. But if you take any single one of those electrons, you can predict with 100% certainty which port it will come out in because we're doing a repeated color measurement. Either it's this color to this color or the top box to the final box. Okay, so we call that a mixed state. And that's going to be in contrast to something called a superposition state. So right now I'll just say versus a superposition state. Okay, and in a superposition state, a single electron that goes into the box cannot be, the output of that one electron cannot be predicted with 100% certainty. Okay, so notice there's a difference between saying any given electron has a 50-50 probability of being measured blue versus I have 100 electrons and 50 of them are blue and 50 of them are white. Also, I think it's very important that we clarify and are really explicit about the following point. When we draw output numbers like 50-50 or 70-30 or so on, those numbers, they represent the true probabilities and they are not accounting for fluctuations that you would see if you actually did the experiment a small number of times. So for example, if we flipped a fair coin 10 times, we would expect half the time we get heads and half the time we get tails. But if you actually do the experiment, it's actually not so common to get 5 heads and 5 tails exactly, right? You might get 3 heads and 7 tails, you might get 6 and 4 and so on, even though it is a fair coin with a 50-50 head-tail probability. Okay, so when we write down a diagram like this, okay, we are saying that if 100 electrons come into this hardness box, we have a 50-50 probability that those electrons are going to come out the hard and soft port. But if you actually did this experiment, maybe it's 45 and 55 or 60-40 and so on. So we're not accounting for statistical fluctuations on a given experiment. We're only talking about the kind of underlying probabilities, which are exact calculable numbers. A nice consequence of the repeatability of a measurement is that you can construct a set of particles with a known property, so a known value for that property. So for example, let's say we had a source of electron whose property for color was, whose value of color was undefined or unspecified, or we just didn't know what it was. We could shoot those electrons into a color box and look at the output of those white electrons and ignore all of the blue ones. So we ignore all of these, but we transmit all of the white ones. And now if we box that up, we could call that a white electron gun, because every electron that emerges from this device is in a known state of color equals white. Okay, and you could do this, you could rotate this around a little bit and get a blue electron gun, or you can get a hard or a soft electron gun, and so on. So this allows us to prepare a quanton in a known state for subsequent measurement. And we'll make use of this a lot in the future. We'll say something like, we shoot 100 white electrons into a box, and you might be wondering, how do we know that we have 100 white electrons? Well, this is one way that you can do it. You prepare a set of electrons in an identical state of all being white, for example. Okay, this brings us to experiment 2, where we look at sequential measurements. So instead of measuring color and then color again, we'll measure color and then hardness, or vice versa. So we're measuring 2 different properties, one after another. Okay, well, let's say that we have 100 electrons input to the first color box, and that 50 come out of each port. So we have 50 blue and 50 white. We ignore the 50 blue, we just let them get absorbed somewhere and we don't see them again, but we focus on these 50 white electrons. When we send those white electrons into a hardness box, we get the following output: 25 hard and 25 soft. So half of the time a white electron is measured soft, and the other half of the time the white electron is measured hard. So what that tells us is a white electron has a 50% probability of being measured hard and a 50% probability of being soft. And so if you think about that for a minute, what that tells you is that the color white is not a predictor of its hardness, okay? Another way to say that is that color and hardness are uncorrelated properties. If you know the color, that does not give you information about hardness. If they were correlated, then a white electron would be more likely to be either hard or soft. And then you could say, okay, I know it's white, therefore I know something about its hardness. But hardness and color are uncorrelated. If you have a defined value for color, that does not give you any information about hardness. Okay, and again, this is maybe not crazy, and so far things are consistent with the classical world, right? You can have a shoe that is both white and hard, or both white and soft, and similar for blue hard and blue soft, right? So nothing so far is that far outside of our daily experience. Okay, but when we get to experiment 3, this is where things start to get a little strange. So here we go. So a takeaway from experiment 2 is that we see that color and hardness, those properties are not correlated. Okay, so you can repeat various versions of the experiment 2, say measuring hardness and then color, color then hardness, blue and white, and hard and soft, all those combinations. And what you find is if the electron is in a known hardness state, then you will get a 50-50 probability of blue and white for color. If an electron is in a known color state, then you will have a 50-50 probability of getting soft and hard for a measurement of hardness. Okay? The simplest way to say this is that color and hardness are two different properties and they are uncorrelated with each other. Okay, friends, this is where the wheels start to come off the classical physics bus, okay? Experiment 3, the granddaddy of them all. We're going to measure color twice, but with hardness in between. And the schematic here, or the setup here rather, is we're going to send 200 electrons in to the color box, and we get half coming out the blue port, half coming out the white port. So basically here we have a white electron gun. Okay, and we're going to shoot white electrons into a hardness box. By experiment 2, we know that 100 white electrons into a hardness box gives us 50 hard and 50 soft. Okay, we then take the 50 soft electrons that were once already measured as white, and we shoot them into a color box. And as a first question, if electrons and other quantons were really classical particles, what would the output numbers in the second color box be? Okay, well, if you put in 100 white electrons and 50 of them continued to the next color box, you might very reasonably assume that once a white electron, always a white electron. So every single electron that enters the color box, the second color box, will retain its whiteness and emerge from the white port. So our prediction would be 100% of electrons entering the second color box would exit the white port. So in this case, we would have 50 white and we would have 0 blue. That's the classical prediction. Okay. So let's see what happens when you actually do this experiment. Well, we find a very different outcome. We find that 100 white electrons go into a hardness box, 50 are measured soft, those 50 go into a color box, and we have 25 blue and 25 white, even though all 50 of these had once emerged from a white port of a color box. So what that tells us then is that once a white electron, not always a white electron, okay? Somehow this insertion of a hardness measurement between two color measurements perturbs the system in a way that changes the measurement outcomes of the second color measurement. Because remember, if we just did color followed by color with no hardness in between, then every single of those 50 electrons entering the second color box would come out the white port. So somehow the insertion of hardness here changes that outcome. And I think it would be perfectly natural to assume that, okay, well, if an electron goes into a hardness box, the act of making the hardness measurement somehow destroys the color. And so the presence of this box is to blame. And there's some truth to that, but I want you to hold on to that idea a little bit, because when we introduce interferometers, hardness interferometers, what we're going to find is if we recombine the hard and soft outputs into a single beam into the color box, that will change these numbers, okay? And we end up back in the scenario of a repeated measurement. So it can't just be that the physical the physical presence of a hardness box is enough to change the outcome. Something about actually making the hardness measurement itself is what is necessary to make that change. Okay, but for now, the bottom line is that even though an electron used to be white, that does not mean that the electron in the future is going to be white if there was a hardness measurement in the meantime. And unlike experiments 1 and 2, this experiment, experiment 3, is the first time that we see a deviation from classical physics, okay? This is definitely different than what you would expect for shoes that can have a color and a hardness, right? If you have 200 shoes and 100 of them are white, and of those 50 are soft, then you would expect them to stay white even though they are soft, okay? So for classical particles, the value of one property does not alter or destroy or change the value of another property. But in the quantum world, what we're seeing experimentally is that you can have observables, measurable quantities, that are somehow incompatible with each other, so that the measurement of one affects the value of the other. So my takeaway from this is that electrons are not classical particles. In other words, we cannot think of them as just small marbles that behave with defined properties, such as color, hardness, position, and so on. Electrons are quantons, and they behave according to the rules and realities of quantum mechanics. And although those rules and realities are different than our daily experience, that is the way nature behaves. And that is what we know experimentally to be true. And so we have to live with and work with that paradigm. All right, let's see what's coming up next. So let's kind of test our understanding a little bit about quantum measurements of color and hardness on electrons. I have two experiments. One is a color followed by hardness followed by color measurement, and the other is a hardness followed by color measurement. And I'm asking, are these following two experiments equivalent? Okay. So give yourself a moment, pause here, think about this, and write down your answer before continuing. Here's how I think about this question. My thinking about this question is the experiments are equivalent if the probability of emerging from the last color measurement box is the same in both cases, given that an electron has come into that box. So for example, in the first experiment, we see that the probability of exiting the white port of the final box is 50%. We shoot in 50 electrons, half come out the blue port, half come out the white port. And the question is, if we get rid of this first measurement of color, is it still true that a measurement of color in this last box is going to give a 50-50 probability? And the answer is yes, right? Because the rule is if you measure hardness, that measurement is uncorrelated with color. So if you shoot a soft electron into a color box, you are always going to have a 50-50 probability of measuring blue and measuring white. Okay, so somehow the fact that the electron has already been measured as white in the first experiment is irrelevant, because once the hardness measurement is made, that whiteness or color property has been erased, and we end up with a 50-50 probability at the output of the final color box. So I would say yes, these two experiments are equivalent with each other because the exit probabilities in the final stage are the same in both cases, 50-50, 50%, 50%. Okay, so now let's get into some interpretations of experiment number 3. You'll recall we've talked about various ways of thinking about quantum mechanics, various interpretations of quantum mechanics, and we pointed out that as with most undergraduate courses in quantum, we are going to present the so-called Copenhagen interpretation, meaning that until a property is measured, it does not have a definite value. Okay. So the way that we use that idea in experiment 3 is that we say an electron with a definite value for hardness, for example, a soft electron, simply has no defined value for color. Okay, that's the statement. If you know the hardness of an electron, the color of that electron is undefined. And I want to be really clear what I'm saying and what I'm not saying. I'm saying that a soft electron simply does not have a color. I'm not saying that the electron has a color but no human being knows what that value is yet. I'm not saying it's defined, just not yet known. I'm saying it does not have a color. I'm not saying that the electron has a color, but it's kind of rapidly changing or oscillating back and forth from blue to white, and that the measured value depends on like when or how you make the measurement. That's not what's happening, right? Because that would be kind of there would be some probabilistic aspect to that, but that's different than saying a no defined color. I'm also not saying that the atom has a color that gets disturbed upon the final color measurement. I'm simply saying that a definite value for hardness implies undefined value for color. And I like to point out this passage from a textbook by Daniel Steyer called The Strange World of Quantum Mechanics. And he goes out of his way to make this point, and I think it's worthwhile that we all pay attention to it. Here I'm saying that an electron with a definite value of hardness does not have a definite value for color. And we can be a little bit, we have to be a little bit careful about this, because the phrase definite value might be a little bit misleading. So I'll just read it here. When I say an electron with a definite value of hardness doesn't have a definite value of color, what I really mean is that an atom, or in this case, an electron with a value of color, with a value of hardness, doesn't have a color. Right? And this second wording is more accurate, but it's so stark that it makes people really uncomfortable. And so usually I will employ the euphemism of definite value rather than no value. And he says, this is a personal failing of mine, but I can't help it. And I think it's a really interesting way to think about it. No definite value really just means no value. That property has no value. And that, for sure, is not a classical idea. Right? In classical mechanics, in your everyday life, every object has a value for every one of its properties at any given time. You might not know the value, but you could find it out in principle. And even though you don't know it, that does not imply that it doesn't exist. Here we're saying a definite value of hardness implies that there is no value, even in principle, for color. So when I say the wheels come off of the classical bus, this is kind of what I mean. And we have to deal with this apparent reality of nature. So here's a little thought experiment that you can do to kind of test your understanding of what we have just discussed. Let's say you have a friend who would like to build a box to sort electrons, not only by color and hardness, but by the combination of color and hardness. Okay, so this box would have 4 outputs because there's 4 possible combinations of white, blue, hard, and soft. You shoot an electron in, and that electron either comes out the white and hard port, the white and soft port, the blue and soft port, or the blue and hard port. And the question is, can you build this box? All right, so give that some thought, write down your answer, and explain to yourself why you either can or cannot build this apparatus. Well, if you understood and followed experiment number 3, you will know very well that this device is impossible to build, even in principle, right? Because we cannot simultaneously have an electron with defined color and hardness, but that's exactly what this box is requiring us to have. So this box is completely inconsistent with quantum mechanics. There is no such thing as a white and hard electron or a blue and soft electron. You can have a blue electron that is later measured as soft, but at no point in time is it simultaneously blue and soft. Okay, and one way to think about this is if you try to build this box out of color and hardness boxes, there is no way that you can do it. Okay, it is possible for you to build this color and hardness box, or build something that looks like it would work. But if you then take the output, let's say the white and hard output, and you feed it back into the input, if this box was really doing what it's advertised, and an electron came out in both the white and hard state, and you put it back in, it would have to come out the same port again. Okay. But I challenge you to build this device out of color boxes and hardness boxes. You can have as many as you want inside this so-called color and hardness box, and try as you might, you will never be able to come up with a scheme by which this output port fed back into the input would guarantee that the subsequent electron would come out the same port that it did the first time. It just can't be done. Well, give it a try if you don't believe me and see what you can come up with. So I'll close by introducing a term that some of you may have heard before called the uncertainty principle. What we've seen with color and hardness is that they are what we might call incompatible observables. Okay, and they're incompatible because you cannot simultaneously know the value of both of them. And if you measure one, then you lose the value of the other. It turns out that in quantum mechanics, there are many such pairs of observables. Not every observable falls in this category. There are certain properties that you can know simultaneously, but many important ones you cannot. Like, for example, a famous one is the position of a particle and its momentum. In other words, loosely speaking, how fast the particle is moving versus where it is physically, where it's located. And if you know the position of a particle very well, then you necessarily have a large uncertainty in the momentum of the particle, and vice versa. You, even in principle, are not able to both measure position and momentum of a particle. Here, with color and hardness, even in principle, it is impossible to know both the hardness and the color of an electron at the same time. So the disruption by measuring, say, hardness, if you measure hardness, you disrupt color. So if you know the hardness, then we say that the color is undefined, meaning that the electron has no color. Okay. It turns out that this uncertainty principle is a fundamental consequence of a wave-like phenomenon. And because we know that quantons exhibit wave-like phenomenon because of interference effects, like as in the two-slit experiment, we know, therefore, that these quantons will be subject to this uncertainty principle. So it's kind of interesting to see the connection between wave-like behavior in a context that has nothing to do with quantum and this really deep principle of uncertainty and incompatible observables for quantons. Okay, so we have really started to uncover some of the realities of quantum mechanics and the underlying behavior of nature at the quantum scale. Experiment 3 is our first foray into the strange world of quantum mechanics, to borrow a term from Daniel Steyer. And for the rest of the course, we will be focusing on and becoming more competent with this idea of incompatible observables and quantum measurement. In particular, the next topic that we'll be discussing involves a so-called color or hardness interferometer, and it will force us to think very carefully about what is meant by a measurement. Okay, just the fact that an electron goes into a color box, does that constitute a measurement of color? So keep that in your mind, and as we come when we come back together in the next video, that will be the focus for our time together. Until then, my friends, stay safe, be well, and have a blast. Talk to you soon.